This unit introduces a highly specialized training path on the environmental and climatic impacts of forest fires. The participants are guided to develop not only a scientific understanding of the composition of pollutants, combustion dynamics, and atmospheric changes, but also the ability to analyze how fires reshape ecosystems, vegetation patterns, and landscape structures. By the end of this unit, learners will have gained operational skills in interpreting emission data, analytical competencies in linking fire behavior with climate processes, and strategic awareness in designing prevention and land management measures. These are critical competencies for law enforcement officers and managers of protected areas, ensuring that their interventions are based on solid scientific knowledge and aligned with international best practices. This agenda reflects a complete and multidisciplinary approach to the study of forest fires and their environmental consequences. It begins with the scientific foundation, analyzing the composition of pollutants, their emission factors, and how different combustion conditions influence the volume and type of gases released. By including the variability of emissions under favorable and unfavorable circumstances, the program highlights the complexity of quantifying fire-related impacts. From there, the focus shifts to large-scale effects, the rise in emissions during extended fires, the energy released, and the interaction between forest typology, weather conditions, and atmospheric chemistry. This section lays the groundwork for understanding how wildfires contribute not only to regional air quality issues but also to global phenomena such as the greenhouse effect and climate change. The agenda then makes a crucial connection with the ecological dimension. It examines how fires interact with vegetation, influencing biomass, flammability, and post-fire carbon dynamics. It considers the Mediterranean basin as a case study, but also broadens the view to global projections. The role of fire as both a destructive force and an ecological driver of change is emphasized through themes like fragmentation, homogenization, and the creation of vegetation mosaics. Finally, the program turns to applied perspectives, moving from analysis to action. It explores the overall impacts of fire on ecosystems and landscapes while stressing the importance of management and prevention strategies. By concluding with this applied dimension, the agenda ensures that the knowledge developed is not only academic but also directly usable by policymakers, managers of protected areas, and law enforcement agencies engaged in environmental protection. Forest fires are not only destructive events for ecosystems on the ground, but also powerful sources of atmospheric pollution. During combustion, and especially in conditions of incomplete burning, forests release into the air around 200 different chemical compounds. These compounds include gases such as carbon monoxide, methane, volatile organic compounds, and fine particulate matter, all of which have significant impacts on both air quality and human health. The complexity lies in the fact that incomplete combustion does not allow the fuel, in this case biomass, to fully oxidize, producing a mixture of partially transformed substances that are far more polluting. For example, black carbon and polycyclic aromatic hydrocarbons are byproducts that can travel long distances, influencing not only local but also regional and global atmospheric chemistry. From an ecosystem perspective, this transfer of compounds into the atmosphere highlights the multidimensional impact of wildfires. While they destroy vegetation and habitats directly, they also alter the atmospheric balance, contributing to processes such as ozone formation, greenhouse gas accumulation, and cloud modification. For professionals in environmental protection and law enforcement, understanding the scale and diversity of these emissions is fundamental. It provides the scientific foundation needed to evaluate the real cost of fire events, to improve investigative approaches, and to plan preventive strategies that can reduce both ecological and public health impacts. When biomass burns, it releases a wide spectrum of pollutants that strongly affect both air quality and climate. Among the most important are methane and hydrocarbons, which act as precursors for ozone formation in the lower atmosphere, contributing to smog episodes. Then we have carbon monoxide and carbon dioxide. The first is highly toxic and interferes with oxygen transport in the blood, while the second is the main greenhouse gas driving global climate change. Equally relevant are nitrogen oxides, which play a dual role by worsening local air pollution and also accelerating the chemistry that produces tropospheric ozone. Finally, particulate matter, very fine and inhalable, penetrates deeply into the lungs, increasing risks for respiratory and cardiovascular health. The origin of these pollutants lies in the incomplete combustion of biomass. Cellulose and lignin, the two main components of plant material, rarely burn completely, especially under conditions of low oxygen. Added to this are the resins and oils contained in many Mediterranean species, such as pines or eucalyptus, which are rich in volatile organic compounds and amplify the release of toxic substances into the air. Even the organic matter present in the soil participates in this chemical cocktail when heated. For environmental crime investigators and protected area managers, this knowledge is essential. It allows them to connect the type of vegetation and soil conditions to the likely pollutant profile of a fire. In other words, understanding the chemistry of combustion means better evaluating the risks for populations, ecosystems, and the atmosphere itself. When we talk about emission factors, we are referring to a very useful tool to measure the efficiency of combustion during a forest fire. The emission factor expresses the amount of a given pollutant released per kilogram of biomass burned, allowing us to quantify the environmental impact of a fire in scientific and comparable terms. For example, carbon dioxide, CO2, usually ranges between 900 and 1,700 grams per kilogram of dry biomass, confirming its role as the main product of combustion. Alongside CO2, however, we also find carbon monoxide, CO, varying between 10 and 270 grams per kilogram. This gas is an indicator of incomplete combustion. The CO/CO2 ratio is therefore a very important parameter. A low ratio suggests efficient combustion with limited toxic residues, while a high ratio reveals poor combustion, typical of smoldering fires or underground peat fires, which are much more polluting. Equally crucial is the analysis of particulate matter, which has emission factors ranging from 7 to 174 grams per kilogram. Particulate is particularly dangerous because it not only reduces air quality but also contributes to climate forcing by altering the Earth's radiative balance. Moreover, it is one of the most harmful pollutants for human health, causing respiratory and cardiovascular stress. In short, emission factors are not just abstract numbers, they allow investigators and environmental managers to evaluate the quality of combustion, the toxicity of the smoke, and the overall climatic and health impact of a fire. This is why they represent a fundamental tool in both environmental protection and criminal analysis of arson. The variability of emission factors is one of the most important aspects when studying the environmental impact of forest fires. Starting with carbon dioxide, CO2, we observe values ranging from 907 up to 1,740 grams per kilogram of dry biomass. This wide variability depends not only on the type of vegetation but also on the combustion conditions. In fast, hot fires, CO2 emissions dominate, reflecting relatively efficient combustion. On the other hand, carbon monoxide, CO, shows an even wider range, between 10 and 270 grams per kilogram. High values of CO are typical of incomplete combustion, when oxygen is limited and biomass burns inefficiently, producing toxic and climate-relevant gases. This is why the CO/CO2 ratio is such a valuable diagnostic tool. It gives us direct insight into the quality of combustion. A low ratio corresponds to efficient burning, while a high ratio signals smoldering or poorly ventilated fires with higher pollutant release. The role of particulate matter must not be underestimated. With emission factors ranging from 7 to 174 grams per kilogram, it represents not only a local health hazard but also a global environmental one. Fine particles can remain suspended in the atmosphere for long periods, affecting cloud formation and altering the Earth's energy balance. In conclusion, understanding this variability is essential. It reminds us that not all fires are the same. The same amount of burned biomass can produce very different pollutant loads depending on fire dynamics, fuel type, and meteorological conditions. For environmental protection forces and investigators, these parameters are key to interpreting fire behavior and its consequences on health, ecosystems, and climate. The variability of emission factors is one of the most important aspects when studying the environmental impact of forest fires. Starting with carbon dioxide, CO2, we observe values ranging from 907 up to 1,740 grams per kilogram of dry biomass. This wide variability depends not only on the type of vegetation but also on the combustion conditions. In fast, hot fires, CO2 emissions dominate, reflecting relatively efficient combustion. On the other hand, carbon monoxide, CO, shows an even wider range, between 10 and 270 grams per kilogram. High values of CO are typical of incomplete combustion, when oxygen is limited and biomass burns inefficiently, producing toxic and climate-relevant gases. This is why the CO/CO2 ratio is such a valuable diagnostic tool. It gives us direct insight into the quality of combustion. A low ratio corresponds to efficient burning, while a high ratio signals smoldering or poorly ventilated fires with higher pollutant release. The role of particulate matter must not be underestimated. With emission factors ranging from 7 to 174 grams per kilogram, it represents not only a local health hazard but also a global environmental one. Fine particles can remain suspended in the atmosphere for long periods, affecting cloud formation and altering the Earth's energy balance. In conclusion, understanding this variability is essential. It reminds us that not all fires are the same. The same amount of burned biomass can produce very different pollutant loads depending on fire dynamics, fuel type, and meteorological conditions. For environmental protection forces and investigators, these parameters are key to interpreting fire behavior and its consequences on health, ecosystems, and climate. When wildfires extend over very large surfaces, particularly beyond 1,000 hectares, the emissions of pollutants into the atmosphere increase exponentially. The volume of gases released is directly proportional to the surface area affected by the fire. This correlation means that so-called megafires represent not only a destructive event for ecosystems and biodiversity, but also a major source of atmospheric contamination with global implications. A key aspect is the condition of incomplete combustion. Unlike rapid flaming combustion, which tends to oxidize most organic matter more efficiently, smoldering or slow combustion generates a much higher concentration of unburned compounds. In fact, scientific studies show that the amount of gas emitted during incomplete combustion can be up to 8 times greater than that released under full flaming conditions. This has serious environmental and public health consequences. Incomplete combustion is particularly rich in carbon monoxide, CO, volatile organic compounds, VOCs, methane, CH4, and polycyclic aromatic hydrocarbons, PAHs, all of which contribute to air quality deterioration and the formation of secondary pollutants such as ozone. These pollutants not only increase local exposure risks for populations and first responders, but also contribute to long-range transport of contaminants, worsening the global climate impact of wildfires. From an investigative and enforcement perspective, understanding the dynamics of combustion phases is crucial. By linking the type of combustion to the intensity and extension of burned surfaces, specialized police units can better interpret atmospheric monitoring data, assess the severity of environmental damage, and provide judicial authorities with scientifically grounded evaluations of the broader consequences of wildfire events. In wildfire science, it is crucial to distinguish between two main types of combustion: complete combustion and incomplete combustion. Complete combustion typically occurs in conditions where oxygen supply is abundant, allowing organic matter to burn more efficiently. In wildfires, this is often associated with slower-moving flame fronts, where vegetation burns thoroughly, leaving less unburned residue. An example is the surface fire progressing gradually through dry grasslands or low shrubs, producing mainly carbon dioxide, CO2, and water vapor as the dominant emissions. By contrast, incomplete combustion arises when oxygen is insufficient or when fuel is particularly dense and moist, preventing full oxidation. This condition is usually linked to fast-moving flame fronts, such as crown fires that race through coniferous forests or large shrublands under strong wind conditions. In such scenarios, the flames consume fuel rapidly but inefficiently, leading to the release of large amounts of carbon monoxide, CO, methane, CH4, particulate matter, PM2.5, and polycyclic aromatic hydrocarbons, PAHs. These compounds represent a much higher pollution burden and pose severe risks for both air quality and human health. For example, a slow-moving prescribed burn in Mediterranean pine litter may represent mostly complete combustion, releasing predictable emissions and serving ecological management purposes. Conversely, during the 2021 Monteferru fire in Sardinia, the combination of wind, high fuel load, and rapid flame spread produced massive incomplete combustion, which significantly amplified emissions and the transboundary transport of pollutants across the Mediterranean. For investigators and enforcement agencies, recognizing whether a fire involved predominantly complete or incomplete combustion is essential, since it explains both the quantity and the toxicity of the emissions recorded. This distinction also provides insights into the fire dynamics, potential causes, and environmental consequences, guiding both prevention strategies and criminal analysis. When analyzing wildfire emissions, it is essential to consider how environmental conditions directly influence the type and intensity of pollutants released into the atmosphere. Under favorable conditions, such as adequate oxygen supply, moderate humidity, and controlled flame spread, combustion tends to be more complete. In these cases, the main outputs are carbon dioxide, CO2, and water vapor, with comparatively lower amounts of harmful byproducts like carbon monoxide, CO, methane, CH4, and fine particulate matter, PM2.5. This is why controlled burns or prescribed fires carried out by trained personnel under carefully planned conditions usually result in lower emission rates and more predictable atmospheric impacts. By contrast, under unfavorable conditions, the combustion process becomes incomplete. Examples include situations of strong winds, drought-stressed vegetation with uneven moisture content, or extremely rapid flame propagation in crown fires. These unfavorable contexts reduce the efficiency of oxidation and dramatically increase the release of toxic pollutants. In such scenarios, we often see higher concentrations of CO, volatile organic compounds, VOCs, nitrogen oxides, NO, and black carbon, all of which contribute to local air quality degradation and have long-range transport potential, influencing atmospheric chemistry and even climate forcing. For instance, a crown fire in a dense pine forest under dry and windy conditions not only produces massive particulate emissions but also injects them at higher altitudes due to convection columns, facilitating their dispersion over hundreds of kilometers. Conversely, in a low-intensity grassland fire under calm conditions, pollutants tend to remain localized and less harmful. From an investigative perspective, this distinction between favorable and unfavorable conditions is key for forensic analysis of fire events. It helps environmental police and Carabinieri Forestali interpret pollution spikes, cross-check satellite monitoring data, and identify whether a fire resulted from natural processes, negligence, or deliberate criminal action. One of the most important aspects in understanding wildfire emissions is the direct proportionality between the burned surface area and the quantity of pollutants released. Simply put, the larger the fire footprint, the greater the emissions. Large-scale wildfires, particularly those exceeding 1,000 hectares, release vast amounts of gases and particulates into the atmosphere, producing effects that can extend far beyond the immediate burn area and influence regional air quality. A critical factor is the efficiency of combustion. When combustion is incomplete, often due to low oxygen availability, high fuel moisture, or irregular flame spread, the process generates a higher concentration of toxic byproducts. Under such conditions, we observe elevated levels of carbon monoxide, CO, methane, CH4, polycyclic aromatic hydrocarbons, PAHs, and fine particulates, all of which pose serious health and environmental risks. It is particularly significant that slow combustion, such as smoldering fires in peat soils, thick leaf litter, or undergrowth, can emit up to 8 times more gases compared to the so-called live or flaming combustion. For example, while a fast-moving crown fire may quickly release CO2 and ash with relatively less toxic residue, a smoldering ground fire can persist for days or weeks, producing sustained emissions of CO and PM2.5 that degrade air quality over wide areas. From an investigative and law enforcement perspective, these differences matter. Environmental police and Carabinieri Forestali can analyze emission profiles to reconstruct fire dynamics and estimate the ecological and health impacts. For instance, unusually high levels of incomplete combustion products detected in air monitoring stations may indicate deliberate ignition in areas prone to slow-burning fires, thereby offering leads in criminal investigations. This relationship between burned area, combustion type, and emission intensity is therefore central not only to environmental science but also to the operational strategies aimed at prevention, suppression, and accountability in cases of forest fire crimes. This satellite image provides a striking example of how the heat of combustion and the massive pollutants released are directly tied to wildfire behavior and the characteristics of the forest involved. The towering smoke plume illustrates the immense amount of energy being emitted. In typical conditions, wildfires release between 16,000 and 22,000 kilojoules per kilogram of biomass burned. This energy not only sustains the fire itself but also propels pollutants into the upper atmosphere, where they can disperse across vast regions. The fraction of biomass consumed is a critical determinant of both energy output and emissions. In crown fires, where flames engulf tree canopies, the proportion of fuel burned is high, resulting in greater energy release and more complete combustion. Conversely, in ground or smoldering fires, less biomass is consumed at once, but incomplete combustion leads to a higher proportion of toxic byproducts such as carbon monoxide, methane, and fine particulates. Forest typology and stage of development also play a decisive role. Young forests with high-density undergrowth and fine fuels burn quickly and intensely, while mature forests with thick trunks and accumulated litter can sustain prolonged smoldering phases, generating different pollutant profiles. For example, coniferous forests with resin-rich fuels tend to produce higher flame intensities and larger plumes, as shown in this image, while Mediterranean scrublands release a different spectrum of volatile organic compounds. The prevalence of fuel, both in type and in quantity, further influences fire intensity and pollutant load. Where continuous, dry fuel beds exist, combustion efficiency rises, leading to massive plumes like the one captured here, which can inject aerosols into the stratosphere. From a criminal analysis standpoint, understanding these variables helps investigators reconstruct fire dynamics. By correlating satellite-detected plume intensity and pollutant dispersion with ground data, specialized units such as the Carabinieri Forestali can infer whether the fire was fueled by natural accumulation, negligence, or deliberate ignition in vulnerable areas. This integration of satellite observation, fire science, and pollutant dynamics provides a powerful tool not only for monitoring but also for law enforcement and environmental protection. The image of dense forest cover highlights how strongly the emission of pollutants during wildfires is linked to vegetation characteristics and meteorological conditions. Forest cover determines not only the amount of available fuel but also the chemical composition of emissions. For instance, coniferous forests, rich in resins and oils, tend to produce higher levels of volatile organic compounds, VOCs, and particulates when burned, while broadleaf forests emit different pollutant profiles with higher moisture content that can slow combustion. Weather conditions act as a powerful amplifier or mitigator of these emissions. High winds accelerate fire spread, exposing more biomass to combustion and carrying smoke plumes over long distances, while temperature inversions can trap pollutants near the ground, intensifying local air quality hazards. Similarly, drought conditions lead to drier fuels, increasing the likelihood of rapid, high-intensity fires with massive pollutant release, compared to wetter periods where combustion efficiency is reduced. This link underlines the strategic importance of forest prevention and management. Thinning dense stands, removing deadwood, and creating fire breaks reduce the amount of combustible material available, thereby limiting both fire intensity and pollutant production. Preventive silvicultural practices, combined with controlled burns under safe conditions, help stabilize ecosystems and mitigate the uncontrolled release of harmful substances during large-scale wildfires. From an operational perspective, prevention translates directly into emission control. By managing forests proactively, environmental police and forest investigators are not only reducing fire risk but also actively working on the reduction of greenhouse gases, fine particulate matter, and toxic compounds released into the atmosphere. Ultimately, the relationship between forest cover, weather conditions, and emissions emphasizes that effective wildfire prevention is also an essential air quality and public health strategy, making forest management a central pillar of environmental protection policies. Wildfires represent a significant source of emissions that profoundly affect the chemical composition of the atmosphere. When forests burn, they release a complex mixture of gases, many of which act as precursors of tropospheric ozone, a pollutant harmful to both human health and ecosystems. Among these gases are oxides of nitrogen, NOx, carbon monoxide, CO, and a wide variety of hydrocarbons. Each of these plays a specific role in atmospheric chemistry. For instance, CO and hydrocarbons undergo photochemical reactions in the presence of sunlight, reacting with NOx to generate ozone at ground level. This process directly modifies the distribution of tropospheric ozone, with effects that can be both regional and global. On a regional scale, areas downwind of major fire events experience degraded air quality, often measured as spikes in ozone concentrations and fine particulate matter. On a global scale, emissions can remain in the atmosphere for weeks, traveling across continents and contributing to long-range ozone pollution, with documented effects even thousands of kilometers from the original fire source. The impact on atmospheric chemistry is therefore twofold. First, the immediate release of primary pollutants that deteriorate local air quality. Second, the generation of secondary pollutants like ozone, which persist and expand their influence far beyond the fire perimeter. Tropospheric ozone is particularly concerning because, while beneficial in the stratosphere for filtering ultraviolet radiation, at ground level it damages vegetation, reduces crop yields, stresses forests, and causes respiratory and cardiovascular issues in humans. For investigators and environmental police, recognizing that wildfires are not just ecological or territorial emergencies but also atmospheric chemistry events is crucial. Every large-scale fire contributes to shifting the chemical balance of the atmosphere, reinforcing the need for prevention and management strategies that consider not only immediate fire suppression but also the long-term atmospheric and climatic consequences of these emissions. Wildfires represent a significant source of emissions that profoundly affect the chemical composition of the atmosphere. When forests burn, they release a complex mixture of gases, many of which act as precursors of tropospheric ozone, a pollutant harmful to both human health and ecosystems. Among these gases are oxides of nitrogen, NOx, carbon monoxide, CO, and a wide variety of hydrocarbons. Each of these plays a specific role in atmospheric chemistry. For instance, CO and hydrocarbons undergo photochemical reactions in the presence of sunlight, reacting with NOx to generate ozone at ground level. This process directly modifies the distribution of tropospheric ozone, with effects that can be both regional and global. On a regional scale, areas downwind of major fire events experience degraded air quality, often measured as spikes in ozone concentrations and fine particulate matter. On a global scale, emissions can remain in the atmosphere for weeks, traveling across continents and contributing to long-range ozone pollution, with documented effects even thousands of kilometers from the original fire source. The impact on atmospheric chemistry is therefore twofold. First, the immediate release of primary pollutants that deteriorate local air quality. Second, the generation of secondary pollutants like ozone, which persist and expand their influence far beyond the fire perimeter. Tropospheric ozone is particularly concerning because, while beneficial in the stratosphere for filtering ultraviolet radiation, at ground level it damages vegetation, reduces crop yields, stresses forests, and causes respiratory and cardiovascular issues in humans. For investigators and environmental police, recognizing that wildfires are not just ecological or territorial emergencies but also atmospheric chemistry events is crucial. Every large-scale fire contributes to shifting the chemical balance of the atmosphere, reinforcing the need for prevention and management strategies that consider not only immediate fire suppression but also the long-term atmospheric and climatic consequences of these emissions. Carbon dioxide, CO2, and carbon monoxide, CO, emissions from forest fires play a central role in the dynamics of global change. CO2, as a long-lived greenhouse gas, directly contributes to the intensification of the greenhouse effect, trapping heat in the atmosphere and accelerating the process of global warming. CO, on the other hand, though less persistent, indirectly influences climate by altering the balance of atmospheric chemistry and contributing to ozone formation in the lower atmosphere. These emissions not only affect global climate but also drive local climatic modifications. Large amounts of particulate matter released during combustion interact with solar radiation, scattering and absorbing it, thereby reducing the amount of sunlight that reaches the Earth's surface. This phenomenon influences both temperature regulation and photosynthesis processes within ecosystems. Additionally, the particulate acts as cloud condensation nuclei, altering cloud formation patterns and precipitation regimes. The image of burned forests and the dense smoke plumes often observed in satellite data remind us that every wildfire is both a terrestrial and an atmospheric event. The rising smoke columns act as vehicles for CO2, CO, and particulates to spread into the upper atmosphere, where they can persist and travel over vast distances. For environmental enforcement and protected area managers, this knowledge underlines the dual dimension of wildfires: immediate ecological devastation on the ground and the invisible but equally damaging atmospheric consequences. Effective strategies of fire prevention and suppression therefore represent not only tools of territorial protection but also essential measures of climate governance, aimed at reducing contributions to the greenhouse effect and mitigating cascading impacts on local and global weather patterns. Forest fires are not only destructive in terms of ecosystems and biodiversity, but they also exert a profound influence on the local and regional climate system. One of the most critical mechanisms is the modification of albedo, or surface reflectivity. When vegetation is removed by fire, the darkened soil and charred surfaces absorb more solar radiation instead of reflecting it, increasing surface temperatures and intensifying local heating. At the same time, the loss of vegetation drastically reduces evapotranspiration, the natural process through which plants release water vapor into the atmosphere. Without this contribution, the hydrological cycle becomes unbalanced. Less water vapor is available to form clouds, reducing rainfall and amplifying drought conditions. This leads to a chain reaction where the energy balance of the ecosystem is altered, reinforcing the likelihood of further fire events and creating a feedback loop. Scientific studies confirm that these processes contribute to significant changes in climate at the local and regional scale. For example, satellite and field research in Mediterranean and tropical ecosystems show how fire scars persistently alter land-atmosphere interactions, leading to hotter, drier microclimates. Over time, these modifications can expand beyond the burned areas, influencing regional weather patterns and even contributing to desertification processes. The image of burned landscapes, where green canopy is replaced by blackened ground, perfectly illustrates this shift, from a surface that once cooled the atmosphere through evapotranspiration and high albedo, to one that now traps heat and accelerates warming. For protected area managers and environmental enforcement officers, these insights highlight that fire prevention is not just about conserving forests, but also about stabilizing local and regional climates, ensuring resilience against broader climate change. The concept of climate feedback is fundamental to understanding the relationship between forest fires and global climate dynamics. Feedbacks occur when the effects of an initial process amplify or mitigate the process itself. In the case of wildfires, the feedback is often positive. Fires release greenhouse gases such as CO2 and methane, which intensify the greenhouse effect, contributing to rising temperatures. These higher temperatures, in turn, create drier conditions and longer fire seasons, making new fires more likely and more intense. At the same time, other feedback mechanisms include the loss of vegetation that reduces carbon storage capacity and alters albedo, increasing solar radiation absorption in burned areas. This further contributes to local and regional warming. For environmental investigators and managers, recognizing climate feedback means acknowledging that fires are not isolated events but part of a self-reinforcing cycle where climate change and wildfires interact, each making the other worse. Understanding this cycle is crucial for designing strategies that aim not only at suppression but also at mitigation and prevention, breaking the loop of escalating impacts. The relationship between forest fires and climate change is not one-directional. It is a feedback system where each process amplifies the other. On the one hand, fires release large quantities of greenhouse gases, such as carbon dioxide, methane, and nitrous oxides, that directly contribute to global warming. On the other hand, climate change itself creates conditions that increase the likelihood, intensity, and duration of fire events. Rising global temperatures, combined with prolonged droughts, reduced soil moisture, and more frequent extreme weather patterns, generate environments that are highly conducive to combustion. As a result, the fire regime, defined as the frequency, intensity, and spatial extent of fires, undergoes significant changes. Regions that once experienced occasional fires are now exposed to recurring events, while ecosystems historically adapted to low fire frequency are being pushed beyond their natural resilience. This reciprocal influence is already visible worldwide. In boreal forests, increasing temperatures have extended fire seasons by several weeks, while in Mediterranean and tropical regions, the combined effect of climate anomalies such as El Niño has triggered unprecedented fire outbreaks. These shifts not only transform ecosystems but also pose challenges to human health, air quality, and land management policies. In essence, climate change drives more frequent and intense fires, and fires, in turn, accelerate climate change, a self-reinforcing cycle with profound implications at both local and global scales. Breaking this cycle requires integrated strategies of fire prevention, land management, and climate mitigation policies, which is why understanding this mutual influence is crucial for environmental enforcement and protected area managers. When analyzing the impacts of human activities on climate change, it becomes clear that anthropogenic factors play a central role in modifying fire regimes across the globe. Unlike natural variability, these changes are often more abrupt, widespread, and persistent. Direct human contributions include land use practices such as deforestation, agricultural expansion, and uncontrolled urban development at the wildland-urban interface. Each of these activities alters fuel availability, continuity of vegetation, and ignition probabilities. For instance, illegal burning for land clearing or the abandonment of traditional agroforestry practices creates new fire-prone environments, where ignition sources are both more frequent and more damaging. Beyond direct ignition sources, there are also indirect consequences that strongly influence climate. Greenhouse gas emissions from industrial activity and fossil fuel consumption have accelerated global warming, increasing the duration and intensity of fire seasons. Air pollution and particulate matter from human sources further interact with fire emissions, amplifying their atmospheric and climatic effects. Taken together, these anthropogenic impacts modify the fire regime, altering not only the frequency of fires but also their intensity, geographic distribution, and ecological consequences. The result is a feedback loop. Human activities both trigger fires and create the climatic conditions that allow them to spread more aggressively. This dual contribution, direct ignition through poor land management and indirect amplification through climate alteration, demonstrates that effective fire prevention and climate action are inseparable. For environmental enforcement officers, it highlights the importance of integrating criminal investigations, regulatory oversight, and climate policy enforcement into a unified strategy. The Mediterranean basin is increasingly recognized as one of the world's climate change hotspots, where the combination of rising temperatures, declining rainfall, and more extreme weather events is reshaping fire dynamics. Projections indicate a significant increase in water deficit, with plants experiencing severe water stress that weakens their resilience and accelerates the drying of biomass. This shift alters the characteristics of available fuel, making vegetation more flammable and creating the conditions for larger and more intense wildfires. Equally critical are the variations in the fire regime, where not only the frequency but also the seasonality of fires is expected to change. In the Mediterranean, fire seasons are projected to start earlier, last longer, and burn with greater severity. Coupled with intensive land use, such as urban expansion, abandonment of agricultural areas, and tourism pressure, the vulnerability of landscapes increases dramatically. The satellite image of Greece engulfed in flames provides a striking real-world confirmation of these projections. It demonstrates how extended drought periods, combined with accumulated dry fuels, generate massive fire fronts visible even from space. These events are no longer isolated, but part of a regional pattern that affects Italy, Spain, Greece, and beyond, with severe consequences for ecosystems, biodiversity, and public safety. For specialized enforcement units and environmental managers, these projections demand not only stronger prevention and monitoring strategies, but also the development of adaptive land management practices that reduce fuel loads, improve water conservation, and anticipate fire behavior under future climate conditions. The increase in atmospheric CO2 concentrations plays a dual and complex role in the dynamics of forest fires. On one hand, higher CO2 levels stimulate greater biomass production, as many plant species respond with enhanced growth. However, this apparent benefit translates into an accumulation of combustible material in ecosystems. Larger volumes of dry leaves, branches, and woody material significantly raise the flammability of forests, especially during hot and dry seasons. As a direct consequence, we observe an increased frequency of fires, since the landscape contains a higher fuel load that ignites more easily and sustains fire spread for longer durations. Over time, this process does not only increase the risk but also alters the composition of plant communities. Species less resistant to frequent fire events are gradually replaced by more fire-adapted species, which in turn modifies the overall fire regime of the ecosystem. This phenomenon illustrates how climate change and fire regimes are interdependent. Elevated CO2 levels intensify vegetation growth, but under drought conditions, that very biomass becomes the driver of destructive and recurrent wildfires. These changes undermine biodiversity and challenge traditional forest management practices, requiring innovative approaches that combine carbon monitoring, adaptive silviculture, and active fire prevention to mitigate long-term risks. One of the most critical aspects in understanding the long-term impact of wildfires is the dynamic relationship between forest regeneration and atmospheric carbon recovery. After a fire, forests have the natural ability to regenerate through processes such as seed dispersal, resprouting, and soil recovery. During this regrowth phase, vegetation progressively absorbs carbon dioxide from the atmosphere, partially offsetting the massive emissions released during the combustion phase. However, this process is asymmetric. The release of carbon through fire is sudden and intense, while the accumulation through regrowth is slow and progressive, often requiring decades before the ecosystem can reach pre-fire carbon storage levels. This imbalance means that frequent fires can destabilize the carbon cycle, making forests net carbon sources rather than sinks. External drivers such as El Niño events and broader climate change trends exacerbate this imbalance. El Niño conditions are typically associated with hotter and drier climates, which increase the likelihood, frequency, and intensity of fires. This disrupts regeneration cycles and reduces the ability of ecosystems to recover atmospheric carbon. Similarly, global warming modifies rainfall patterns and growth conditions, further affecting regeneration and long-term carbon balance. Therefore, natural regeneration is not always sufficient to fully restore ecosystem services and climate regulation functions. Effective management strategies must integrate post-fire restoration, carbon monitoring, and climate adaptation measures to mitigate the risk of ecosystems shifting toward degraded states dominated by recurrent fires. This slide highlights a particularly important dimension of the global wildfire problem: the geographical and temporal evolution of fire regimes under changing climatic conditions. In the United States, projections consistently estimate a significant increase in burned areas, a trend strongly associated with prolonged droughts, rising average temperatures, and the intensification of heat waves. One critical aspect is the latitudinal shift of vegetation belts. As climate zones migrate northward, species traditionally confined to certain ecological niches are being replaced by others with higher flammability. This creates a dynamic feedback loop, where novel ecosystems may emerge but with greater vulnerability to ignition and rapid spread. A parallel situation is observed in Mediterranean-type ecosystems, not only in southern Europe but also in California, Chile, South Africa, and Australia. These ecosystems, already adapted to recurrent fire, are now experiencing fires of unprecedented intensity and frequency, driven by the combined pressure of climate extremes and anthropogenic land use. This explains why Mediterranean areas are often considered sentinel regions for global wildfire risk. What happens here is likely to foreshadow future trends in other parts of the world. Equally concerning is the extension of the fire season, which is no longer confined to the hottest summer months but is expanding into spring and autumn. This expansion reduces the recovery time for ecosystems, increases suppression costs, and places fire management agencies under sustained pressure throughout the year. From an academic perspective, these observations confirm that wildfires are not isolated disturbances but structural drivers of ecological transformation. They reshape landscapes, alter species composition, and redefine the resilience of ecosystems. For policymakers and environmental law enforcement agencies, such as the Carabinieri Forestali, this evidence underscores the urgency of adopting adaptive management strategies, integrating fire prevention with climate adaptation policies, and preparing for scenarios where fire is no longer an episodic event, but a permanent component of environmental risk management. First considerations. The slide offers the opportunity to introduce one of the most debated and, at the same time, promising approaches in modern environmental management, prescribed fire. Wildfires undoubtedly exert a strong influence on both climate dynamics and vegetation patterns, often acting as a destructive force that accelerates ecological transitions. However, when carefully planned and controlled, fire can also serve as a management tool rather than just a threat. This is where the concept of prescribed fire becomes essential. Prescribed fires are intentionally set under controlled conditions to reduce fuel loads, prevent catastrophic wildfires, and guide the regeneration of ecosystems in a way that aligns with conservation objectives. In ecological terms, fire is not only a disturbance but also a catalyst of change. It clears the understory, recycles nutrients into the soil, and allows fire-adapted species to thrive. Mediterranean ecosystems, for example, evolved with fire as a natural component, and the absence of fire often leads to excessive biomass accumulation, creating the conditions for extreme and uncontrollable events. From a climate perspective, prescribed fires can reduce greenhouse gas emissions in the long run by limiting the probability of megafires that would otherwise release enormous amounts of carbon dioxide, carbon monoxide, and methane into the atmosphere. In addition, by influencing vegetation composition, they can contribute to stabilizing the balance between carbon storage and carbon release. For environmental management and law enforcement agencies such as the Carabinieri Forestali, the role of prescribed fire must therefore be integrated into adaptive fire management strategies. It requires accurate risk assessment, robust scientific data on fuel conditions, and strong interagency coordination to ensure both safety and ecological benefit. In conclusion, fire should not be considered exclusively as a destructive phenomenon, but also as a strategic ally in managing landscapes, mitigating climate risks, and shaping the future of vegetation dynamics. The challenge lies in discerning between fire as an uncontrolled disaster and fire as a planned ecological instrument, and ensuring that society, through science and governance, learns to master this distinction. Fire is widely recognized as a key ecological driver in Mediterranean ecosystems, where it has shaped landscapes and species dynamics for millennia. Unlike other disturbances, fire does not simply destroy, it conditions the structure and composition of vegetation, influencing biodiversity patterns and ecological processes at multiple scales. In the Mediterranean environment, fire creates a mosaic of regeneration and degradation stages, generating spatial heterogeneity. After a fire, some areas rapidly regenerate with pioneer or fire-adapted species, while others undergo slower recovery or even degradation, depending on soil quality, intensity of the event, and recurrence of disturbances. This patchwork effect has profound implications. It maintains species diversity, creates ecological niches, and conditions the distribution of both plants and animals. At the same time, fire directly influences the landscape structure. By periodically resetting successional stages, it prevents the dominance of single vegetation types and promotes dynamic equilibrium between forests, shrublands, and grasslands. For instance, Mediterranean pines regenerate quickly after fire through serotinous cones, while oaks and other hardwoods rely on resprouting, highlighting the species-specific adaptations that co-evolved with frequent burning. From a management perspective, acknowledging fire as an ecological factor rather than an external anomaly is essential. Suppression alone cannot be the answer, as it often leads to fuel accumulation and catastrophic events. Instead, fire must be integrated into conservation strategies, where both natural fire regimes and prescribed burns are considered tools to maintain ecological resilience. In conclusion, the Mediterranean landscape is not only resilient to fire but also shaped by it, with the resulting mosaic of regeneration stages acting as a natural regulator of biodiversity and ecosystem processes. Ignoring this role means misunderstanding one of the central mechanisms that sustain Mediterranean ecosystems. Wildfires are increasingly recognized as one of the most disruptive drivers of landscape change, not only because of their immediate destructive impact but also due to their capacity to push vegetation away from its potential natural state. In ecological terms, the potential vegetation of an area refers to the plant communities that would establish in the absence of major disturbances, given the local climate, soil, and topography. Fires, especially when recurrent or particularly intense, disrupt these trajectories, preventing ecosystems from reaching their potential stability. In recent decades, the scale and frequency of wildfires have grown significantly, largely due to the combination of climate change, land use pressures, and accumulated fuels from decades of fire suppression. These fires are not isolated events, they represent systemic shifts that profoundly alter ecosystem structure and function. Ecologically, repeated large-scale fires can lead to loss of biodiversity, soil degradation, and an increased dominance of fire-adapted but often less diverse plant communities. Economically, the costs of suppression, restoration, and lost ecosystem services, such as carbon storage, timber production, and ecotourism, are immense and growing. Another key aspect is the alteration of landscape structure. Where once a heterogeneous mosaic of forest, shrubland, and grassland maintained ecological resilience, repeated fires can simplify the landscape, creating vast uniform areas more vulnerable to erosion, invasive species, and subsequent disturbances. This homogenization reduces ecological stability and undermines long-term ecosystem services. Thus, wildfires today must be understood not only as natural ecological processes but also as phenomena increasingly driven by human and climatic factors, with profound implications for landscape dynamics. Effective management requires strategies that acknowledge this duality, integrating prevention, controlled use of fire, and ecological restoration, to counteract the negative ecological and economic effects of increasingly extensive and frequent. One of the most significant long-term consequences of repeated wildfires is the transformation of the landscape. After a fire, areas that were once dominated by trees often undergo a shift toward shrub-dominated ecosystems. Initially, shrubs may colonize burned surfaces as part of the natural regeneration process, but when fires become too frequent or too intense, this succession is interrupted, and forests may fail to recover. Instead, the landscape evolves into dense, shrubby patches that are highly flammable and prone to recurrent ignition. This process leads to the creation of a fire-prone mosaic, where the dominance of shrubs increases the probability of fire spread. Shrubs typically have higher surface-to-volume ratios than trees and retain volatile oils, which act as accelerants. Consequently, the landscape itself becomes a fuel bed, reinforcing a vicious cycle. The more fires occur, the more vegetation shifts toward shrubs, and the more likely further fires become. This feedback loop not only increases the risk of ignition but also amplifies the intensity and dynamics of fire propagation, creating conditions for larger burned areas. From a landscape ecology perspective, this represents a form of structural simplification. Where once there may have been a stratified forest ecosystem with multiple layers, trees, understory, ground cover, after repeated fires, we often observe a predominance of a single shrubby layer. This reduces biodiversity, alters habitat availability, and decreases ecological resilience. Moreover, the connectivity of fuel loads across the landscape increases, enabling fires to travel more easily across large areas. Thus, wildfires do not simply destroy vegetation in the short term, they reconfigure landscapes in the long term, transforming them into fire-adapted, yet ecologically fragile, systems. For protected area managers, this shift highlights the need for proactive fire management, including controlled burns and vegetation interventions, to prevent landscapes from evolving into permanent high-risk fire environments. The passage of fire through a forested area does not merely destroy, it also transforms the landscape, creating what ecologists describe as a heterogeneous system. Instead of a uniform structure, the post-fire environment is characterized by a patchwork of burned, partially burned, and unburned areas. This heterogeneity is fundamental because it generates a diversity of habitats that can support different species at various stages of succession. What emerges is a form of dynamic balance, where processes of regeneration, such as seed germination, resprouting, and recolonization, coexist with processes of degradation, including soil erosion, vegetation loss, and structural simplification. Rather than being static, the landscape continuously shifts along this spectrum, influenced by fire frequency, severity, and interactions with climate and human activity. A key outcome of this transformation is the promotion of fragmentation. Large, continuous forest stands may be broken into smaller patches, increasing the heterogeneity of the landscape. While fragmentation can reduce connectivity for some species, it can also create ecological niches that favor others, leading to greater biodiversity in the short to medium term. Therefore, fire acts as a structuring force, reorganizing ecosystems into mosaics of differing resilience and vulnerability. Recognizing this dual role, both destructive and creative, is essential for land managers, as it highlights the need for adaptive strategies that balance conservation goals with the ecological reality of fire-driven landscapes. The immediate ecological effect of fire is often paradoxical. On the one hand, we observe a rapid increase in herbaceous vegetation, which quickly colonizes the burned surface thanks to seed banks in the soil or wind-dispersed species. This flush of herbaceous cover provides short-term stabilization for soils and prevents severe erosion, but it also introduces a more uniform vegetative structure. At the same time, fire produces a decrease in overall vegetation diversity. Shrubs, trees, and other slower-covering species are often eliminated or severely reduced, resulting in a simplified ecosystem dominated by fast-growing herbaceous plants. This reduction in structural and species diversity has cascading effects on fauna, limiting available niches and reducing ecosystem resilience. Importantly, research shows a strong relationship between landscape uniformity and fire frequency. Homogeneous landscapes, dominated by a single type of vegetation or age class, are far more susceptible to recurrent and intense fires. By contrast, heterogeneous landscapes, where patches of herbaceous, shrubby, and forested areas coexist, tend to slow fire spread and reduce overall intensity. Therefore, the fire's role is twofold. It triggers an immediate shift toward herbaceous dominance while simultaneously setting the stage for longer-term dynamics of recovery or degradation, depending on the frequency of subsequent fires. If fires occur too often, the system risks being locked in a cycle of low diversity and high susceptibility, with herbaceous vegetation replacing more complex forest structures permanently. The relationship between fire frequency and landscape structure is fundamental for understanding long-term ecological dynamics. When fires occur too frequently, the landscape tends to become monotonous and simplified. Continuous burning prevents the establishment of more complex vegetation layers, trees, shrubs, and successional mosaics, and instead favors species that regenerate quickly and uniformly. This repeated cycle drives the system toward homogeneity, with reduced biodiversity and lower ecological resilience. On the other hand, large but rare fires have a different effect. They often create vast areas of uniform vegetation recovery, as entire landscapes are reset simultaneously. The result, again, is a tendency toward homogeneity, though produced by infrequent, high-impact events rather than continual disturbance. By contrast, fires of modest size and limited extent can actually promote fragmentation and diversity within the landscape. These smaller-scale disturbances generate a patchwork of burned and unburned areas, creating a mosaic of habitats at different stages of regeneration. This heterogeneity provides niches for a wider range of plant and animal species, thereby supporting biodiversity and buffering the ecosystem against future disturbances. From a management perspective, the key is to avoid both extremes, neither excessively frequent small fires that lock the system into monotony, nor catastrophic megafires that homogenize large regions. Instead, a regime of controlled or naturally moderate fires can maintain the desired balance of fragmentation, heterogeneity, and ecological resilience. When examining the impacts of wildfires on landscapes, it is crucial to consider the different plant types involved. Mediterranean pine forests, broadleaf species, shrublands, and grasslands all respond differently to fire. Some species, such as pines with serotinous cones, are adapted to regenerate after burning, while others, such as old-growth broadleaf stands, may suffer irreversible losses. The selectivity of fire effects is particularly important. Fires rarely act uniformly, their intensity and spread vary across terrain, fuel loads, and microclimatic conditions. This means that some areas may experience complete canopy destruction, while nearby zones retain unburned patches, creating a mosaic of ecological outcomes. Such heterogeneity shapes post-fire regeneration dynamics and the long-term structure of the landscape. Equally significant is the extent of the fire. Small fires may have localized effects, but large-scale events, so-called megafires, radically transform ecosystems, fragment habitats, and disrupt ecological corridors. The severity of the fire determines whether the landscape undergoes temporary disturbance, with eventual recovery, or a permanent shift toward different vegetation types, often more flammable shrublands. In sum, the combination of plant types, selective burning, spatial extent, and severity defines the trajectory of landscape modifications. Understanding these interactions allows land managers and environmental agencies to design more targeted restoration and prevention strategies, ensuring ecosystems maintain resilience in the face of increasing fire pressure. Wildfires fundamentally reshape the natural landscape, introducing structural changes that manifest across both space and time. Vegetation composition is altered, fauna are displaced, and natural habitats are often destroyed or fragmented. These impacts vary according to ecological context. In mountainous regions, fires may accelerate erosion and reduce soil stability, while in lowland forests they may shift ecosystems from tree-dominated communities toward shrublands or grasslands. The spatial and temporal diversity of these consequences is striking. Immediately after a fire, we often see scorched vegetation and a loss of biodiversity. Over time, however, the effects extend into altered regeneration dynamics, new successional pathways, and sometimes permanent changes in land use potential. The same fire event can have very different ecological legacies depending on local conditions, fuel types, and climatic influences. Because of this variability, management and prevention become critical. Without proactive strategies, such as risk mapping, fuel load reduction, and restoration planning, the negative impacts of fire may dominate, reducing ecosystem resilience and ecological services. Conversely, with well-designed control strategies, it is possible to limit degradation, guide regeneration, and preserve both biodiversity and landscape functionality. Ultimately, these dynamics highlight that fire is not only a destructive force but also a driver of ecological change, one whose consequences must be anticipated and actively managed through long-term planning and adaptive strategies. Fire profoundly modifies the structure of natural landscapes, acting as both a destructive and transformative force. Its impacts are not uniform but vary significantly across space and time, depending on factors such as vegetation type, topography, and local climatic conditions. For example, in some Mediterranean areas, frequent fires convert forests into shrublands, while in other regions the same event may trigger a slow process of soil degradation and biodiversity loss. The consequences extend beyond vegetation. Wildlife habitats are destroyed or fragmented, forcing fauna to migrate or adapt to new conditions. This alters species distribution and can disrupt ecological networks. Importantly, these impacts evolve over time. The immediate destruction caused by flames may be followed by long-term changes in soil fertility, erosion rates, and the regenerative capacity of ecosystems. For this reason, effective management is essential to mitigate negative outcomes. Planning must integrate both short-term interventions, such as rapid response and rehabilitation of burned areas, and long-term strategies, including sustainable forest management, controlled fire use, and restoration of ecological corridors. Preventive measures, when properly implemented, help maintain landscape resilience, ensuring that fire acts as an ecological factor without escalating into an environmental disaster. In essence, fire's influence on the landscape highlights the importance of planning, preparation, and adaptive management, allowing societies to reduce risks while preserving the ecological integrity of natural systems. Active land management is one of the most effective tools available for wildfire prevention and for safeguarding ecological health. By acting proactively rather than reactively, it is possible to significantly reduce both the frequency and the intensity of fire events. Prevention strategies include fuel management through controlled burns, vegetation thinning, and the creation of fire breaks, all of which aim to limit the spread and destructive power of flames. These practices, when combined with systematic monitoring, help ensure that risk areas are quickly identified and addressed before conditions escalate into large-scale emergencies. Long-term planning plays a complementary and equally vital role. It involves integrating fire prevention into broader territorial and ecological policies, ensuring that land use, forestry, and conservation strategies all contribute to maintaining the landscape's dynamic balance. This means designing resilient ecosystems, where vegetation mosaics and species composition are managed to reduce vulnerability to fire. In turn, this not only protects biodiversity but also preserves the ecological services on which local communities depend. Ultimately, wildfire prevention is not a set of isolated interventions but part of a continuous management cycle, in which planning, monitoring, and active stewardship work together to anticipate risks and maintain the health of ecosystems over time. By embedding prevention into long-term strategies, societies are better prepared to adapt to climate change and to mitigate the ecological and social costs of wildfires. Active land management represents a cornerstone in the conservation of ecosystems and in the prevention of natural disasters. In landscapes increasingly exposed to climate change and anthropogenic pressures, the implementation of prevention strategies is essential to reduce both the frequency and the intensity of wildfires. Constant monitoring of the territory, through satellite systems, drones, and ground patrols, ensures the timely detection of critical situations, allowing rapid interventions before small ignition points evolve into large-scale events. Equally important is the role of long-term planning, which must go beyond emergency response and aim at maintaining the dynamic equilibrium of the landscape. This includes the diversification of forest structures, the introduction of fire-resistant species, and the careful regulation of human activities that increase ignition risks. In Mediterranean environments, for example, the mosaic-like management of vegetation is crucial to reduce fuel continuity and thus slow down fire propagation. Furthermore, adaptation to climate change becomes an unavoidable requirement. Rising temperatures and prolonged droughts amplify fire hazards, making it necessary to design flexible strategies that can evolve together with changing environmental conditions. Ultimately, active land management does not only mitigate risks but also strengthens ecosystem resilience, ensuring the preservation of biodiversity and the protection of communities living in vulnerable territories. Fire must be recognized as a crucial ecological factor, not only as a destructive force. In many ecosystems, including Mediterranean and boreal environments, fire plays an essential role in natural regeneration. It clears accumulated organic matter, opens seedbeds, and facilitates the germination of fire-adapted species. This regenerative role highlights that fire is not inherently negative, but rather a natural process that, when balanced, supports the renewal and resilience of ecosystems. At the same time, the impact of fire on landscape structure and diversity is profound. Fires reshape the spatial composition of habitats, creating mosaics of burned and unburned patches. These mosaics support species heterogeneity, offering niches for pioneer species while allowing late successional species to re-establish in other areas. However, when fire regimes exceed ecological thresholds, becoming too frequent, too intense, or too widespread, this regenerative capacity weakens, leading to degradation, biodiversity loss, and shifts toward less resilient ecosystems such as shrublands. Therefore, sustainable management strategies are indispensable. These strategies must aim to preserve the natural role of fire while mitigating the risks associated with uncontrolled wildfires. Tools such as prescribed burning, fuel load reduction, and adaptive landscape planning allow managers to harness the ecological benefits of fire while protecting human communities and infrastructure. The challenge lies in striking a balance, acknowledging the ecological necessity of fire while reducing its destructive potential in the face of climate change and land use pressures. Ultimately, preserving the natural environment requires integrating scientific knowledge, advanced monitoring technologies, and proactive management policies. By doing so, we can ensure that fire continues to contribute to landscape diversity, ecological function, and long-term sustainability rather than driving irreversible damage.
Thank you for your attention.